So today we are going to use mean field approximation to learn something about Coulomb interactions for many electrons. So the system we have is a crystal. There are ions that are localized at lattice points. And then there are electrons that are all around them. The kinetic energy of the electron, we can write it in terms of second quantization. We can solve the non-interacting part of the Hamiltonian. And what we will get is a bunch of states. We'll use Pauli's exclusion principle. And we defined something called Fermi momentum. What that means is all states that have momentum less than Fermi momentum are occupied, and all states that have momentum larger than the Fermi momentum are empty. So this is the picture for non-interacting part of the Hamiltonian. Next, we want to add interactions, and we want to see what happens. We discussed that this is, in general, a very complicated problem. It involves 4 operators, and they are difficult to treat. So we discussed an approximation on Friday, which essentially it's called mean field theory. And the approximation is that we assume that the deviation from the average value of a pair of operators is small. And we discussed on Friday how this can be used to develop a simpler Hamiltonian. And we discuss it for the case when we have 2 distinct type of particles. And we derived the mean field Hamiltonian, and we discussed that perhaps the most important constraint on this mean field theory is imposing the self-consistent criteria. And we'll learn in the next few lectures, we'll see that this really restricts the value of the expectation, the value that this expectation value can take. So the self-consistent criteria is a very stringent criteria. You can guess any value, but when you go through the procedure, you usually find that there are only few values that are allowed. So now let's assume that we have fermions, electrons, and I'm going to write down the Hamiltonian we are interested in. H0 is the usual non-interacting energy. V interaction, this is the Coulomb interaction. So how to write Coulomb interaction in this way? We discussed this in the first 2 lectures of the course, and we use the same notation. These quantum numbers, nu prime, mu prime, think of them as momentum eigenstates. So we'll choose momentum eigenstates for our second quantization. Now, the idea is to simplify this term because this is difficult to treat. So let's try to do mean field theory. Any questions? So let's try to develop a mean field theory by taking these 4 operators and what we are going to do is we are going to replace these 2 operators by the following. We're going to subtract the expectation value from this and add Now, just as we did last time on Friday, we'll define this quantity as deviation operators, and I'm calling it d mu prime. So this quantity can be written as d mu prime plus expectation value c mu dagger c mu prime. Then I will be left with this operator c nu dagger c nu prime. This I'm going to write again as c nu dagger c nu prime. I will subtract the expectation value and add. And this I will call the deviation operator nu prime. So finally, I can write this as d mu prime, d nu prime, plus the product of expectation values. Now, the mean field approximation is setting this quantity to 0. And by doing this, you will get the mean field Hamiltonian, which is really, you can write now again in terms of operators, which really just involves two particle operators now. So you have c mu dagger, c mu prime, So we derived a mean field Hamiltonian, which is basically replace the interaction term by this guy, this line. It has 3 terms. The last one is just a constant. Now, this is a perfectly valid Hamiltonian. You can start with this Hamiltonian, calculate these expectation values in a self-consistent way, and use this Hamiltonian to model your system. It turns out that this is not a very good model. And then naturally we want to improve the model, and we ask why, what are we really missing in this theory? And the one way to see that this is not a very good model is to look at this 4 operator term again and recall Wick's theorem. So if we have these 4 operators, c nu dagger, c mu dagger, c mu prime, c nu prime. Now let's try to take expectation. Let's take expectation value of these four operators in the non-interacting ground state, in the ground state of just a single particle terms, just to get a feeling of what this term really does. So this expectation value denotes expectation value in the Fermi sea. So this is what we discussed last thing on Friday. So we showed that this is equal to 2 terms. So I'll just write down the result. The key thing here is the only way this quantity can be non-zero is if all of these quantum numbers, nu, nu prime, mu, mu prime, are momentums less than kf. How? So this is the Fermi sea. What does this operator do? This destroys an electron with nu prime. Now, if the momentum is greater than kf, you'll get zero. That state is empty. You cannot destroy. So the only way you can get finite is this nu prime is less than kf. Now you have, if you started with n particles, you have n minus 1 particles. Now, again, annihilation operator with mu prime. If mu prime is greater than kf, you'll get 0 because there is nothing there. Mu prime must be less than kf. So we've shown that these two are less than kf. And now you have n minus 2 particles. Now you create 2 particles. And first you create a particle with mu. So if mu is greater than, so now to create 2 particles, you must create these 2 particles at the same place with the same momentum labels that you destroyed or you annihilated. Only then you will get a non-zero overlap with this state here. So in this way, we have shown that all these 4 labels must be less than kf. But you destroy 2 particles, you can create in any order. And as a result of that, you get 2 terms. So this quantity is equal to C nu dagger, C nu prime, C mu dagger, C mu prime, minus C nu dagger, C mu prime, and C mu dagger, C mu prime. So this is basically, we have included all the possible contractions, and we get these 2 terms. We showed this on Friday in detail. So now we can see from the right-hand side that there are actually 4 ways to define deviation operators. One is d nu nu prime. We have used that. D mu mu prime. We have used that. But there are also, you can define d nu mu prime, which is these operators minus its expectation value, and d mu nu prime. Those deviation operators do not appear in our approximation yet. So to improve our mean field theory, we will consider another term, and we'll add another term to our Hamiltonian, which will account for this term coming from Wick's theorem. So now let's do the same thing. I'm not going to go through all of the steps. Consider this term, C nu dagger, C mu dagger. So this term that we started with, just use anti-commutator and reverse the order of these 2. So this is minus C nu dagger, C mu prime, C mu dagger, C nu prime. Now this quantity you can write as deviation operator nu mu prime plus the expectation value of plus this guy. This you can write as deviation operator mu nu prime plus expectation value of that, and then expand the whole thing, kill the product of 2 deviation operators, assuming it to be small. What you get from here is minus C mu dagger, C nu prime. So this operator times the deviation operator, and then simplify the whole thing. The final Hamiltonian would be this. So this term is called the Hartree term, and this term is called the Fock term. So if you don't include the Fock term, you would be missing quite a lot. In principle, we'll see later on in the course that to get ferromagnetic state for this, there are some solids that are ferromagnets. Use them on your fridge. To explain this ferromagnetism, or the quantum theory of this ferromagnetism, you need to have this Fock term. And we can add this to the Hamiltonian, or we can improve our model to include these correlations motivated by the Wick's theorem. Yes? Yeah, this, and this, the three terms. So, well, let me just write down everything then. So the total V interaction, it can be written as Hartree plus the Fock term, the Hartree term we can write this as half. Now I will insert so right now we just did operators. I will insert these matrix elements now. So this Hartree term is mu prime, nu prime, V, mu prime, and I will in a minute. So this expectation value, I'm using this notation, nu prime. Yes.
I might have missed this, but do the subindices include a spin label or?
Yes, that's a very good question. So later on, for the moment, so you can assume that there are momentum and spin, and this is the general Hartree-Fock theory. Next, what we are going to do is we are going to assume that there is no spin, and then later on, when we discuss ferromagnetism, we'll insert spin and see what happens. But for this general form of Hartree-Fock Hamiltonian, these indices include spin. Yes.
So where you've written the Hartree term and the Fock term, like when you actually derive them, the left-hand side of the equation is the same in both cases, right?
Let me try to understand what. So yeah, so there is this operator, which can be written like this.
That's the same as the operator that you've got for the Fock term.
Yes, yes.
So why are we adding them together if it's...
So that's just to improve our... So it's not... let me put it this way. So if we only keep this... So the motivation is to replace these four operators by expectation values of two operators. Now we know... So, but we still want to keep this four operators as operator. So what we want to get is on the right-hand side, we should still have operators multiplied by expectation values. What we know from Wick's theorem is that in general, when we take expectation value of this, we get two terms. And this is just a way to include both of terms by considering two separate terms to begin with and do mean field theory on them separately. This is just one way to derive this. The main idea is, again, we want to write down these four terms, take pairwise terms and replace them by their expectation value plus something, or deviation around their expectation value. And what Wick's theorem tells us is there are 4 deviation operators that are relevant. And this is just one way to derive it. Yes?
Shouldn't there be a 1/2 factor for each of these? It might be interactive.
So you mean this, or?
Well, like adding another 1/2 because each of them will give you exactly the form of the interactive potential, right?
I think so. There is no 1/2 here. So I mean a factor of. So this factor of half is included to avoid double counting.
No, but
You already have it there.
your original expression has a 1/2 anyway, so he's saying
Yeah.
we have another, like an additional 1/2 factor because we basically have 2 of these same terms that we write down in different ways.
No, so let me try to explain why. So the idea is that you can destroy 2 particles, but you can create in any order, and both of them will give you non-zero expectation value. So this term is actually sum of 2 terms in terms of expectation value. It is sum of 2 terms where you first destroy 2 particles. In one term you create in one order, and in the other one in the other order. Also, don't worry much about factor of 2s at the moment. So it's just an approximation. And if there is, say, additional factor of 2 or any scalar constant, when we will impose the criteria, the self-consistent criteria, you will see that if you added some additional factors, all that will play no role. Because right now, you can add a factor of 2, but essentially, you see there are these numbers, these n nu prime, these are expectation values. What are these? We don't know yet. We will calculate them self-consistently. So if there are some additional factors, you will see later on that when we impose this stringent self-consistency criteria, all these factors will go away. Any other questions? So we can simplify this a bit further. Let me close these brackets. We can write down now, we forget spin, let's consider spinless electrons. And for spinless electrons, you can use the tricks you used in tutorial 2 to write down this Hamiltonian K1, K2, or this term K1, K2, K3, K4, K1, K2, K3, K4, C, K3 dagger, C, K4 dagger, C, K2, C, K1. This quantity can be written as sum over, instead of 4, you can write it, you can basically use conservation of momentum to get rid of one momentum sum. V tilde Q, where this is now the Fourier transform of the potential, interaction potential. So this you showed in tutorial 2. Use similar tricks. You can write down the interaction term in this way. The reason I'm doing this is to simplify So right now we have 4 sums. We want to build some intuition into this, what these Hartree and Fock terms do. So we want to use conservation of momentum and get rid of one momentum sum. So now V Hartree will be half sum over P prime Q. Instead of these nus and k's, I'm going to stick to p's and q's. V tilde Q So in the rest of the class, we want to understand this Hartree term and this Fock term in detail. So all I've done in writing this is I use conservation of momentum. First, I suppress the spin index. So nu prime, mu prime, they're only momentum. And then this is from tutorial 2. You can use conservation of momentum, get rid of one momentum sum, and I can simplify the Hartree and Fock terms in terms of these two. Now, the last term for both of them is just a constant. So if we are just discussing the Hamiltonian, a constant in the Hamiltonian does not play any role. So in the dynamics, so we can forget, we are going to ignore these two terms.
Question?
Yes.
Is that assuming that you already found the self-consistent solution?
No, not yet. So the idea is to that's actually the next thing. That's the next big thing. What are these numbers? So I say this is the Hartree-Fock Hamiltonian, but still includes these ends. What are these ends? So what values they take, and this is where self-consistency will play an important role. So to make further progress, as you mentioned, we have to now decide what these ends are. So this is where a lot of physical insight will go into developing this Hamiltonian. So what values? So the question we want to ask is CK dagger, CK prime. What values can this take? So you have, for example, there you had NP minus QP and I hope you can all read P prime plus QP prime. So these momentum indices. Now the question is what values these can take. So you have to assume certain things. Now this is where you start putting in approximations, which must be good approximations. And one way to see that they're good approximation is to try to gain some insight about the ground state that you're trying to explain using this model Hamiltonian. So the idea is you have state of matter, you have state of a system, you have, say, some experimental data about it. If not, just assume that there is some state of matter that exists. You want to develop a simple Hamiltonian that describes this state, and then you can use this Hamiltonian to calculate any correlation function that you're interested in, and then make predictions about what will happen if you apply some stimulus to the system, what will be the response of the system. So you have to put in you have to use some insight from the ground state that you're interested in explaining. One approximation, for example, we can make is that this C K dagger CK prime, which by the way we are calling N K K prime. So I put in commas here just because there were too many labels. So this is our notation. This is called NKK prime. One approximation is to say that this is delta KK prime NK. Now this is just an approximation. What does this approximation mean? This approximation means that the ground state respects translational invariance. So if in the ground state you annihilate a particle with certain momentum k or k prime, you must create the particle with exactly the same momentum for this to be non-zero. So the ground state respects momentum conservation. This is just an approximation, yes.
But even if it respects momentum conservation, wouldn't we have additional delta terms with reciprocal lattice vectors?
Yes, so you can have terms with the reciprocal lattice vectors, for example, and in that case, you will have k and then k plus g, k plus g, and g is a whole lot of vectors. Let's assume we restrict our discussion to first Brillouin zone. In that case, k and k prime, they're both in the first Brillouin zone. It is possible that you have additional terms. So what I want to say is this is an approximation. In fact, we know there are condensed matter systems. One particular example is something that is called the charge density wave. And in this charge density wave, for example, you will have, so what happens is the ground state can spontaneously break translational invariance. So you start with the ground state that respects momentum conservation, translationally invariant. You can undergo a phase transition. The system will undergo a phase transition and it will spontaneously break translational invariance. To understand what charge density wave really means, for example, just to make sure, so I want to make sure that you understand that this is where a lot of approximation is going in, a lot of thought is going in deciding what to put here, what to put for these expectation values. So let's take an example where, so let's consider these ions here, something that we did earlier, so we can use the same example. So these are a bunch of ions. Now these ions are positively charged. They will attract some electron density. So there is electron density, say, around here, and there's another ion electron density. So if I want to plot electron density as a function of x, this is the position axis, I have some electron density. Let's assume that this is actually uniform. So there are ions, they will attract electron density close to it. All of these ions do this, and as a result, you get a uniform electronic density, just as an example. So we discussed Peierls instability, which told us that a one-dimensional system is unstable at half filling. So if you are at half filling, what will end up happening is one of the ions will either move to the left or the right. Let's assume it moved here. This one moved here. And this one moved here. Now you see in this region, there are no ions. So they are not going to attract electronic density. As a result, you will get something like this now for electronic density. You'll get something like, you'll get a dip here. You can also think of it as just step function. So the key idea is now ions, there are no ions here. So you could get a state, a ground state of the system where the electronic density has a wave-like shape. And in this case, let's call this to be lambda. Let's assume this distance is lambda. So the momentum corresponding to this, let's say, is q. So in this particular case, this nkk prime, it would be delta k, k plus q, nk, k plus q. What that means is, in the ground state, you have electronic density at many points. You can annihilate a particle from electron density here and create one here. And the system, it's a wave, it's a periodic system. So the translation invariance is broken, but there is still discrete translation invariance. As in, the system is translationally invariant by a translation of lambda, or in momentum space q. So this quantity would still be, or actually this is the quantity that will be a good candidate for the mean field theory. Now in this particular case, as you said, if you figure out this lambda will turn out to be a reciprocal lattice vector, but you can have some other systems where this need not be a reciprocal lattice vector. One system is, let's imagine some complicated crystal, and as a result of the complicated symmetry of the lattice, the Fermi surface is such that it has many branches, and it is called nested Fermi surface. Think of it like nested dolls. You have two layers of Fermi surface, and these two layers are separated by some momentum in this reciprocal space. Corresponding to this momentum or this wave vector, you can have a charge density wave. So we know in condensed matter there are systems such that the translation invariance in the ground state is spontaneously broken. So this is just an approximation. Yes?
That expression for nkk prime, you don't have k prime.
Yeah, so I mean, I'm just assuming that this was k prime in general, but now it's restricted to k plus q. So k prime equal to k plus q, where q is the wave vector corresponding to charge density wave. So if the notation, just ask, because there are too many things. If you find the notation sloppy, just please ask. Any other questions? On in here. So here, this is the general quantity. This is just a number. And here I assume that k and k prime must be same. And in that case, I can just drop one k prime. And it is again notation. So with this in mind, let's stick to this. Stick to this for the moment. So let's assume that the ground state respects momentum conservation. It's a big approximation, but let's assume that. That means that we are assuming that we are not close to a phase transition to a charge density wave, for example. So with this approximation, NPQ is basically delta PQ NP. Now put this in these two Hartree and Fock expressions, drop the last two. So I will just do the Hartree term, and so what you will find is you have factor of half, sum over P prime, because of this delta function. Another another momentum index will disappear, and you will have V tilde now 0, C P prime dagger, C P prime N. Actually, now that let me just put this back. There is no harm in for the moment. We'll simplify notation later. Plus CP dagger, CP N P prime P prime. This is what I get for the Hartree term. I've ignored the constant term. So you can see how this appears. Basically, we have NP minus QP, the first term. Because of this criteria, Q must be 0, and you directly get this term. And this is from the second term. Again, Q must be 0. And this is simply because of the assumption that ground state is translationally invariant. Now, in this term, you can exchange P and P prime. They're dummy labels. What you will find is that V Hartree is actually sum over PP prime, V tilde 0 is N PP, CP prime dagger, CP prime. So this is why now this half disappears. There are two terms, they're both same. Now, so far we have made assumptions about the ground state, and we've derived the Hartree term. Similarly, we can get the Fock term. Now, this V tilde 0, this is something you will see a lot in physics, not just in condensed matter, at a lot of places in high energy theory also. Let's look at what this really means. So we define V tilde Q. This is the Fourier transform. So you have 1 over omega e to the power I Q dot R V of R P cube R. Now this, you probably have already done this in field theory. You can do this integral. One way to do this is to assume Q is along Z and then integrate over the whole space. So what that means is you have 1 over omega, you have an integral e to the power I mod Q, and then now I'm using spherical coordinates, R cosine theta, angle between them. V of R is E square let's say 4 pi epsilon naught r. Then you have r square sine theta d theta d phi and dr. Now you can cancel one r, but you will see that still there is a divergence. The integral is diverging in the sense that when r goes to infinity, there is a divergence in this integral. This is called the infrared divergence, and this appears at many places in physics. And this divergence at r equal to infinity, or r going to infinity at long distances, when you do this Fourier transform, you can show that v tilde q, this goes as 1 over mod q square. So keep doing this integral and you can show that it's, well, I think this was also in tutorial 2. So this goes as 1 over mod q square. So this infrared divergence, r going to infinity, means in momentum space, when q goes to 0, there is divergence. So we wrote the Hartree term. What appears here? The Fourier transform with 0 momentum. And that is, there is a divergence here. So in a moment, we'll discuss how to deal with that. Whenever there is a divergence, the divergence is there in our theory. In physical system, when you measure something, you'll never find something that is diverging. So there is something that we have overlooked in our model. So we'll go back and fix that and try to make sense of why this was diverging in first place. And for the moment, so we'll do that in a minute. Let me just write down the Fock term also. And the reason I'm doing that is to see if Fock term has a divergence also. So we see that the Hartree term has this well-known infrared divergence. Let's look at the Fock term. So the Fock term, you can also write it using this approximation here, that the ground state respects translation invariance. You can write this as sum over p prime, v tilde, p minus p prime, cp dagger cp, Now again, these two terms are equal to each other. The trick, you can interchange p and p prime and use that v tilde p minus p prime is same as v tilde p prime minus p, because essentially it only depends on the modulus. As you can show from this integral. So only depends on the modulus. So V Fock is simply minus. I will now write this as sum over PQ. V tilde Q minus P and QQ CP dagger CP. So actually, the Fock term also has the infrared divergence. So we have two sums, PQ. When Q is equal to P, we have the Fourier transform with zero momentum, and we know that diverges. So now I can write down the total Hamiltonian H as sum over P epsilon P plus sum over Q V tilde 0 minus V tilde Q minus P N QQ CP dagger CP. Now, this Hamiltonian has only single particle terms. So this is the original dispersion. To this original energy, non-interacting energy, you have to add something that depends on interactions. And this whole quantity is defined, what you have added to the Hamiltonian. This is called self-energy. So what have we achieved so far? We started with 4 particle terms. We went through the whole derivation of mean field theory to write it down as expectation value times 2 operators. When simplified some things, we got rid of 2 momentum sum, and we finally arrived at simple expression for Hartree term and Fock term. And in this Hamiltonian, I've just combined all of the results. So I have the single particle term, the original single particle energies, the kinetic energy, for example. This you can think of as h bar square p square over 2m. And now to this, I have to add something that depends on interactions. And now this whole Hamiltonian still has only single particles. So in condensed matter, we'll call these new particles. So their energy is no longer just this. The single particle energy is no longer just this, but you have added something which we are calling self-energy. Now, if you consider this whole thing as the single particle energy, we'll call these new particles with this as the single particle energy as quasi-particles. The reason we are calling these new particles as quasi-particles is that they have very different properties from the original single particles. So you remember this schematic of mean field theory that we drew in the sketch? There was a box with a lot of particles, and you can get rid of all of the particles, just keep one particle in the presence of average density due to all other particles. This one new particle is not same as the original single particles. So now we have single particle term in the Hamiltonian that describes quasi-particles. Now, there is more on this in the tutorial, I think tomorrow. In the tutorial, you will discuss more about this. One important thing to think of is if this whole quantity now, you can imagine this whole quantity, not just the self-energy, but self-energy plus this as, so if you think of H as sum over P, H bar square, P square over 2, M star, CP dagger CP. So think of this whole thing as buried into the new mass of the quasi-particles. So in the end, after doing all this approximation, you get new particles, let's call them quasi-particles, that have very different mass as compared to the original mass. In the tutorial, you will use Hartree-Fock theory, and you'll discuss properties of this, of effective mass. You'll see that there are cases where this can have very interesting properties and consequences. So interactions essentially play a very important role, and this is one way to deal with it. Now let's not forget that it's all good on, it looks good on board for the moment, but we are forgetting that there was a divergence. So we still have to deal with this infrared divergence. So next I'm going to discuss how to deal with this divergence. So, yes.
Can you always guarantee that the self-energy term will be proportional to momentum squared, like to get that effective mass out? Or?
Yeah, so this is essentially we are defining this. Let's call this whole quantity as this quantity.
Okay, so does the effective mass depend on?
Yeah, and it really you can define it in different ways also. So some people will define it not having this p here at all, and say you don't have Fock term, then some dependencies will go away. But it really is a matter of definition. So the self energy at the moment is diverging. The quantity that you're adding is diverging. So this is not physical, simply not physical. So how do we deal with this infrared divergence? Well, so we remember in condensed matter systems, the way we will deal with them is something called screening. What that essentially means is so remember that we have many particles, we have many electrons, we have many charged particles, we have many electrons, many ions. So if you want to calculate, first I'm going to discuss classical theory of screening. You can also do a quantum theory of screening that takes a bit more effort, and depending on how much time we have in the third week, we'll discuss the consequence of quantum version of what I'm going to present. But the classical version is very easy to understand, and using that intuition, we can make sense of these divergences. So imagine that you want to calculate electric field of system. So you put a test charge. So imagine that there is a test charge, a unit positive charge. You want to calculate electric field due to this test charge at some point r. So the question is, what is this electric field? Well, you can calculate it, use Coulomb's law, and calculate the electric field. Now, in our system, we have many electrons. And remember that these electrons are mobile. In fact, we calculated the velocity of these electrons. The electrons at the Fermi level, for example, have the velocity, Fermi velocity. So the velocity is defined as dE over dk. So calculate the derivative of energy with respect to momentum, and you can find out the effective velocity. So we have many electrons that can move around. As a result of that, this positive test charge is going to attract some negative electronic density around it. As a result of this, the electric field at this point r is going to be much smaller than what it would have been had there been no other electrons. And the simple phenomena is called screening. So the electric field is going to be diminished. Now what that essentially does is, so Coulomb interaction is long-ranged. That means electric field is going to be finite even when r is very large. But now, because of screening, this electric field is going to get diminished when you are very far away. So screening converts long-range interactions into short-range interactions. Short-range meaning that the effect can only be felt for small distances. Any questions? We can do the same thing for negative charges. Say you want to calculate electric field due to this. Now, what will this negative charge do? This negative charge is going to repel electronic density around it. If the electronic density around it is repelled, remember there were immobile ions or ions that were moving very little. Those ions are still in the background. Positively charged ion. As soon as you expel electronic density around these, the positive charge of the ions is now going to screen this charge. And again, you will get, starting with long-range interactions, effectively, you will get short-range interactions. Any questions so far? Okay, so this is just a physical picture of screening. And we want to use this insight to make sense of the infrared divergence. Now, one way, so what we have learned from this analysis is that there is a divergence as r goes to infinity because the Coulomb potential is long-ranged. And screening will make this Coulomb potential into a potential that is short-ranged. So one model potential that you can use to replace Coulomb interactions, the long-range one, is what is called Yukawa potential. So next, what we can use is Yukawa potential. Which is essentially screened Coulomb potential. So the Yukawa potential, you basically have this potential E square over 4 pi epsilon naught r. This r, we can see if you just have this r, there is a divergence, there is infrared divergence. One way to get rid of this is to multiply this with an exponential. Where kappa naught is what we will call or define as Thomas Fermi screening wave vector. So the reason we are using Yukawa potential, so Yukawa potential when this, if there is no wave vector, no screening, kappa naught 0, it becomes the Coulomb potential, which has infrared divergence. But now if you put in this potential, in this integral here, and try to calculate the Fourier transform, you will find that V of Q now for this Yukawa potential is no longer diverging. So the tutorial tomorrow, you have a problem on Yukawa potential. You will use this potential and then discuss what implications you have for the effective mass for the quasi-particles that you will obtain using this expression. Any questions? Yes?
Do you know how to estimate these constants for the properties of the material we have?
So there are ways to find it. So this is related to polarizability of the system. So essentially, this is related to dielectric properties of the system. Or you can think of, so okay, physically, what is relevant is the mobility of electrons. Electrons have to be mobile to screen these charges. So this mobility shows up in conductivity of the system and is related to dielectric function. So we'll discuss some of this in the third week And when we try to calculate conductivity using, say, Kubo formula or something, so there are ways to derive screening or screening length. So the inverse of this wave vector is the screening length. So what essentially means it's a measure of how quickly this effectively the electric field will disappear. But for the moment, let's just assume that you know this from some experiment. So experimentally, you can try to see how far you can go and still feel the electric field. And let's assume that you figured it out, and that took the inverse of that gave you the screening wave vector. Any other questions? So with this, I will end the discussion of Hartree-Fock theory. So we've learned fair bit. We have learned that we can, at least there are, under some simple assumptions about the ground state, you can develop a simpler model for the system, for which the Hamiltonian only contains single particle terms. All the effect of the interactions or all the correlations are now included in self-energy. This is still a model, this is still an approximation. Sometimes it works, sometimes it does not. For Hartree-Fock theory, this has been successful in explaining quite a lot of materials. So this is a more successful theory. It applies to many materials. In principle, you can use this theory to explain what is called, or some properties of what is called electron gas. Essentially metals. A lot of metals can be explained using Hartree-Fock theory. Yes?
In 2D materials, the Coulomb potential is logarithmic.
Yeah.
So then does the Yukawa potential still work, or is there a different screening?
So there are other, Yukawa potential is just one way of doing it. In 2D, you will already see that, as you said, you don't have this R, but you will have logarithmic divergence. And the divergence is, in some sense, not as worrisome to begin with. But there are other, so to answer, there are other ways also. But in 2D, the phase space is also small. So, but there are typically, so it depends again on the material. Say you take some material which has a lot of free electrons, for example, graphene. If there are a lot of mobile electrons, if the system has high mobility or two-dimensional electron gas, then still you can have, you will have screened Coulomb interactions, and you can still use a version of Yukawa potential. So if there are mobile charges, so I would say this, that screening is a physical phenomenon. If there are mobile charges, there will be screening. And that will convert a long-range interaction into a short-range one. That's in general true. Any other questions? So we have seen the power of mean field theory so far in explaining electron-electron interactions. In the case when the ground state is relatively simple, that it respects translation invariance. Another place where mean field theory is very useful is when you want to study phase transitions. The reason is the following. So how do we define phase transitions? So we have two phases. In one phase, let's define a quantity called order parameter. In a phase transition, you can think of this phase transition as going from a disordered phase to an ordered phase. And now you can define something called an order parameter. This order parameter is going to be 0 in the disordered phase and is non-zero in the ordered phase. So you calculate expectation value of this order parameter in the two phases, and if it is 0, you'll say this is the disordered phase or phase 1, and if the expectation value of the order parameter is non-zero, this is phase 2 and there is a boundary between them. So if you want to study these phase transitions, what you need to do is you need to calculate expectation value of order parameters. Now, if we choose order parameter to be something like this, that goes into the mean field theory, then this expectation value, there is a stringent criteria coming from self-consistency. So if this is our order parameter, to calculate expectation value of the order parameter, you will, when you impose self-consistent criteria, you will deduce that there are only certain values that this order parameter can take. And you are interested in finding when this expectation value is non-zero, because that corresponds to the second phase. So to find out where this expectation value is non-zero, you can use self-consistency criteria within the mean field theory. So the main point I want to say is mean field theory is extremely useful to study phase transitions. And we are going to now discuss one particular phase, which is called ferromagnetic phase. So we want to discuss a quantum theory of ferromagnetic state. So we know the normal state is like metallic, and we know the ferromagnetic state. What we know, or our intuition tells us, that all of the spins are aligned in the ferromagnetic state. So we are going to use this bit of intuition to discuss the ferromagnetic state. So the question we want to address is, when does a system of, say, electrons becomes ferromagnetic? What value of interaction strength? For example, we had Coulomb interaction here, and the strength of interaction is given by V tilde Q. What values of interaction strength gives you ferromagnetic state? So what we'll find out is that the Fock term plays an important role for ferromagnetic state. If you did not include Fock term to begin with, you would not get any spin polarization or a ferromagnetic state. Any questions so far? So next, what we are going to do is use mean field theory to explain ferromagnetism. This is also called Stoner model for ferromagnetism. So let me write down the Hamiltonian that we are interested in. So we are not going to start with the full form of Coulomb interaction. We have seen that screening makes this long range into short range one. Let's go to the extreme version where you only have point-like interactions. That means in real space, the interactions are finite if you're sitting on top of each other. They are point-like. It's a delta function interaction in real space. So in momentum space, the Fourier transform, it's just a constant. What that means is I can write down the full Hamiltonian, full in the sense that I'll write the single particle terms and the two particle terms. The full Hamiltonian is sum over K and sigma. And now I'm going to put the spin index back in the Hamiltonian. So K sigma psi K, CK sigma dagger Ck sigma plus u over 2 omega sum over k prime q sigma prime So what have I done? I've assumed that VQ, so this you can relate it to where we started in the Hartree-Fock theory, but I've essentially assumed that the matrix elements of the interaction potential, so that has 4 momentums. When you write it in terms of 3 momentums, you have Fourier transform, and we have assumed that this Fourier transform is a constant. And it's a constant, and it's denoted by U. So U is the interaction strength. So the interactions does not depend on momentum. So what does that mean? In real space, you have a point-like interactions. And this omega is the system volume. So this is the model Hamiltonian that we are starting with. We already made some approximations. Motivated by screening, we are now considering extremely short-ranged interactions. The reason we are making these assumptions is with these assumptions, you can solve the mean field theory in a very easy way, and we are going to figure out, we will impose the self-consistency criteria on this, and we want to answer the question depending on these parameters, u and psi k, for what values of u will the system be ferromagnetic? So that's the question we want to address. Now, this model is also known as Hubbard model. Well, it is known as Hubbard model. Now, this is fermionic. All these operators are fermionic. You can also, there is a Hubbard model for bosons also, where all these operators are bosons. But we are only interested in fermions at the moment. So all these operators are fermions, just like before. So this is called the Hubbard model, and we are going to start here. So next, what I'm going to do is something similar what we did in Hartree-Fock theory. I'm going to make some approximations so that I can move forward with the mean field theory. So what I'm going to do is I'm going to assume that this expectation value Ck sigma dagger, Ck sigma prime or K prime sigma prime, this is delta sigma sigma prime, delta K prime, n K sigma. What does this mean? It means that I'm assuming that in the ground state, all spins, so all spins are, say, in one direction, are polarized. That will mean that if you annihilate a spin sigma, or upspin or downspin, you create the same spin. Sorry. So mathematically, this is what we are going to assume. And this approximation already imposes 2 constraints on the ground state. One, again, that the ground state respects momentum conservation or translational invariance. And now with these delta functions for spin, if you destroy spin sigma and you create spin sigma, this also imposes the time invariance. So we expect this. So what we expect is for a ferromagnetic state is that this time invariance will be spontaneously broken and all spins would be aligned in one particular direction, either spin or down. There will be more spin density of one kind than the other, and there is some net magnetization. But to start with, we can make this assumption. This seems like a reasonable choice. And again, this is just an assumption that we are going to start with. And then we are going to calculate, when we calculate this, when we impose the self-consistency criteria, this is essentially, you can think of this as just when you are guessing the expectation value. And to make the guess, we're just trying to make this guess in as clever way as possible. Any questions so far about notation or anything? So what this means is, well, let me define another thing, which is 1 over omega sum over k n k sigma. This I will define as n sigma, where sigma is up or down. So this is defined as spin density. So I will call this n up, n sigma, and up and n down, I will call them as spin density. And in the ferromagnetic state, I would expect that the spin density of up electrons is not same as spin density of down electrons. Any questions? So if we use this, using this approximation, we can again put this in the Hubbard model. And now, again, we are going to get a Hartree term, which means the term that corresponds to using 2 deviation operators, and then the Fock term, so there are total 4 deviation operators. Hartree contains 2, Fock contains 2. We'll go through the same procedure again and derive the mean field Hamiltonian for corresponding to the Hubbard model. Any other questions? Okay, so if we go through this algebra, and you can show that you can write the interaction term, that is the second term in the Hamiltonian, the Hartree part. Now I'm going to use this definition for so what does that mean? I will write down the deviation operators d k sigma k prime sigma prime as c dagger k sigma c k prime sigma prime minus the expectation value, and go through the whole thing. What I will find is that the Hartree term is u over 2 times omega sum over k prime q sigma prime c k plus q dagger sigma c k sigma. And now I'm writing this. Actually, again, let's simplify this notation further. Actually, let me keep it this way and let me tell you in words what I mean by this. So this is what you will get from the Hartree term. Just if you look at the 4 terms there, the 2 terms in the center, C dagger K prime minus Q sigma prime, C K prime sigma prime, define a deviation operator using them, and you will get this term, then the other term, and then this the constant. What I mean by this index here is that the expectation value that I've used, so I've replaced 4 operators by 2 operators times an expectation value, and in the expectation value I have these indices. That's the notation. So just go through the algebra, you'll find this. And similarly, you can write the Fock term, which you'll obtain by anti-commuting the last 2 and then going through the whole thing again. You will find minus u over 2 omega and now we can put in these definitions. So in all of these terms, you have this quantity n, and you have a sum over momentum, and you have these delta functions. And when you put all this, I will write down the result, and tomorrow we are going to start from that result. So putting these definitions into this result, you can show that the interaction potential can be written as u over 2 omega So you would see that in the Hartree term, the spin indices would be same to begin with, and you would not have any delta functions. But in the Fock terms, you will have these delta functions, sigma, sigma prime, coming from here. And this will have an important consequence for ferromagnetism. So go through the algebra till this point. We'll start here and try to make sure that you see that the Hartree term does not have these delta functions, and in the Fock term, you must keep these. So the full Hubbard model, you have the kinetic energy part, and you have these two terms. The first line corresponding to the Hartree, and the second line corresponding to the Fock term. So tomorrow we'll start from here and see how this Fock term will give rise to ferromagnetism. Any questions? Yes.
Why did you assume that the potential is a delta function?
This is just to make our lives easy. So just to simplify the calculation, the motivation comes really from screening. Screening, we have seen that it converts long-range potential, Coulomb potential, into a short-range one. And now we are just taking an extreme version of it where it's just extremely sharp like a delta function. So just to ensure, well, so the approximation has been made so that I can solve the equations on board and gain some insight. In reality, if you don't have delta functions, you have to stick to whatever form you have. It can be some complicated function of position. As a result, the momentum Fourier transform in momentum space, it would be some complicated function, and still the intuition we'll develop from this model will apply to a more general case.